Priya. Welcome to my YouTube channel Life in Chemistry. I have already uploaded the part 1 question solve of previous year CSIR NET questions of the chapter Inner Transition Elements. I hope you can get lots of information from that video. Let's continue the next part. In this part, the first question is, consider the ions Aurum-3, Gadolinium-3, Samarium-2 and Lutetium-3. The observed and calculated magnetic moment value. That is, we have to consider these three inner transition elements and we have to look at mainly the observed and calculated magnetic moment value. And the main point asked in the question is closest for the pair. That is, we need to determine the observed and calculated magnetic moment for those pairs which has closest observed and calculated magnetic moment. That is, we need to determine mu observed equivalent to mu calculated. Okay? So let's check the options given below. To know the answer properly, we have to need the main concept behind the magnetic moment of the inner transition element. The magnetic moment of inner transition elements, that is lanthanides, depends mainly on the orbital magnetic contribution and spin magnetic contribution. That is, mu depends on both L and S values. Okay? And we have to consider both orbital angular momentum and spin angular momentum. That is L and S, where capital L is the summation of L1 plus L2 plus L3 plus L4 plus ... And capital S is a summation of S1 plus S2 plus S3 plus S4 plus . Okay? But the main fact which shows the magnetic moment in any such compound is the number of unpaired electrons present in a compound. Okay. So let's do the question. From the given options, we can see there is a 4 pairs. One is a gadolinium-3 and lutetium-3, another one uranium-3 and lutetium-3, samarium-3 and gadolinium-3 and samarium-3 and uranium-3. At first, we all know that gadolinium-3 has the electronic configuration of 4f That is 4f7. Okay, and lutetium-3 have the electronic configuration is 4f14. Okay, and or 4f7 and 4f14. Aurum-3 has electronic configuration 4f6 and samarium-3 has electronic configuration 4f5. Okay, so as we know, f orbital can achieve total number of electrons is 14, and when f orbital is half filled, it has 7 electrons on it. That is, if f orbital bother 7 electrons, it is half filled. And if it has 14 electrons, then it should be fulfilled. Okay, so let's check the electronic configuration of gadolinium-3 and lutetium-3. Gadolinium-3 plus, as we mentioned before, that it has electronic configuration 4f7, and lutetium-3 plus has electronic configuration 4f14. Okay, and that is, it is a half filled and it is full filled. And due to that, all lanthanides has both orbital magnetic moment and spin magnetic moment contribution, and according to that contribution, the effective magnetic moment of lanthanide is mu equal to G root over J into J plus 1, where G can be determined from this expression. Okay, and there is an exception for in case of gadolinium 3 plus, and its effective magnetic moment is calculated by the expression mu equal to root over 4s into s plus 1 plus l into l plus 1. Okay, but this is followed by the gadolinium 2 plus electronic configuration, because it has four f7 5 E1 6f0. Okay, but for gadolinium 3 plus, due to the electronic configuration 4f7, that is half filled, it has no significant orbital magnetic contribution. It has no significant orbital magnetic contribution. That's why the observed and calculated value is equal for gadolinium 3 plus. That is nothing but the mu spin only value. That is root over n into n plus 2, where n is number of unpaired electron. Okay? So, we also can say from the electronic configuration of lutetium-3 plus that it has fulfilled 4f14 electronic configuration, which also has not such observable magnetic moment due to the orbital angular momentum. That is the capital L value. Okay, then we can say the answer should be option A. Let's come to the next question. The next question says the correct electronic configuration and spin-only magnetic moment of gadolinium-3 plus. As we already mentioned, the electronic configuration of gadolinium-3 plus is 4f7. Okay, 4f7. Okay, and for that it is half full. That is, there is a n equal to 7. That is number of unpaired electrons. And from here we have to determine the spin-only magnetic moment. That's why the formula to determine the spin-only magnetic moment is mu s equal to root over n into n plus 2. Now put the value of n in this equation. We have the value root over 63, which is near to the square of 8, that is 64. That is, the square root of 63 should be less than 8, that is near about 7.9 according to the given option. Now let's see the correct option mentioned here is 7 xenon 4f7 7.9. Okay, we can say the answer is option A. Now let's do the next question. The next question says, consider the following lanthanide 3 ions. Okay, which ion? Iridium 3, gadolinium 3 and das. And we have already mentioned that the magnetic moment produced to the spin-only value is shown by the gadolinium 3 and lutetium 3. There is no option of lutetium 3, so there is no chance of having the option iridium or dash. The option should be A. So let's do the next one. Identify the pairs in which the covalent radii of elements are almost similar. Okay, let's check the given options or given pairs, that is niobium and tantalum, molybdenum and tungsten, lanthanum and lutetium, and scandium and yttrium. As we know zirconium, hafnium, niobium, tantalum, and molybdenum tungsten. These pairs shows almost similar covalent radii due to lanthanide contraction effect. Okay? Due to lanthanide contraction effect, they show almost similar covalent radii. That's why we can easily say the answer should be niobium. Answer should be niobium tantalum and molybdenum tungsten. That is A and B. Answer is option A. Now let's do the another question is the ground state forms of samarium 3+ and uranium and aurum 3+ respectively. Okay. So the ground state forms of samarium 3+ and aurum 3+ respectively. For samarium 3+, we have the electronic configuration is europium, the samarium 3+ and europium 3+, and for samarium 3+, the electronic configuration is xenon 4f65d0 and 6s0. From that, we can say the number of unpaired electrons, that is n equal to 6 here, which achieves the following f orbital, 4s shells, and from that we can get the L value, that is 3, and for 3 as we know, for S that is 0, for P that is 1, for D that is 2, and for S that is 3. That L equal to 3 means term is capital F. Now we have to determine the 2L plus 1 value. The 12 plus 1 value is 7. Okay? And as we already mentioned, n equal to 7. That's why n equal to 6. So S equal to 6 by 2 equals to 3. Okay? And as it is less than half filled, we know that J equal to L minus 7 for less than half filled, and J equal to L plus S for greater than half filled. Okay? As here that is less than half filled, J should be L minus S, that is 3 minus 3 equal to 0. That's why the time is 7s0, and from samarium 3+ is 7s0. So as we have mentioned respectively, so we can easily choose our correct answer, that is nothing but option A. Now the question says, which of the following statements true for the lanthanide? So the main point we have to notice here is true statement for lanthanide. So we have to carefully read all the statements given below at first. The first statement is the observed magnetic moment of Europium-3 plus at room temperature is higher than that of the calculated from spin orbit coupling. Okay? As we know, Europium 3 plus has electronic configuration 4f6. Okay, that is less than half fill. For that, it has both contribution of orbital angular momentum and spin angular momentum in case of magnetic moment. From that, we can say at room temperature, the calculated spin orbit coupling magnetic moment spin or during the calculate from the calculation, the observed value will be greater. That is, the option A is correct. Next statement is lanthanide oxides are predominantly acidic in nature. As we all know, if we go left to right, in case of periodic table, acidity increases. Okay. And basicity decreases. As lanthanide oxides are mainly left at left side comparatively in periodic table, so it has basic nature rather than acidic nature. So that statement is wrong. So let's check out the next statement, which says that the stability of samarium-2 is due to its half-fill subshell. Let's check the electronic configuration of samarium-2. Samarium-2 has electronic configuration xenon 4f6, 5d0, 6f0. Okay, that is 4f6. It is less than half fill 4f7. So this statement is also wrong. Let's check out the last option. Lanthanide 3 ions can be separated by ionization chromatography. As we all know, it is true. So, statement A and D is true. So, the correct option is option A. I hope this video also can help you in your upcoming exam preparation. I will be grateful to you if you suggest me for further further solving process, and I will be glad if you all encourage me, and please like, comment and share as much as you can, and not forget to subscribe my channel Life in Chemistry and ring the bell icon. Okay, meet you guys soon. Bye bye. Thank you to all of viewers.